Welcome to probability distributions. So far we've learned about descriptive statistics and we've delved a little bit into probability, and we're going to use both of those techniques and knowledge bases to work with probability distributions. Now, a probability distribution is very similar to just a frequency distribution or any other kind of display of data. A probability distribution, however, is something that describes the likelihood that something will happen, not how much something actually did happen, right? When we have a frequency distribution, it shows how many times a certain piece of data actually showed up in our data set, whereas a probability distribution gives us each probability or likelihood that a particular data value will show up in the future. That's the big difference. So here's a little picture showing that when we have some data, there's kind of two things we can do. We can have our descriptive statistics where we can put our data into a table. So in this example, they're looking at people who had 2 kids, and of those 2 kids, X here represents the number of them that are girls, right? So out of 2 kids, they either had 0, 1, or 2 girls, and this was the frequency of how often that happened. And then we can calculate an average and standard deviation, and it kind of makes sense that the average value of X should be pretty close to 1, right? Because that would be the average number of girls possible out of 2. And then down here we can actually figure out the probability of each, the probability of having no girls, 1 or 2 in 2 births. And that would be a very simple 2- technique of 1 out of 2 and 1 out of 2. That would be if they had to both be girls, and there's your 1/4 or 0.25, and then you get the same thing if they were both boys, and then the rest over bit would be the 1. Well, we put that all together, and so again, X is our number of possible girls, and then we list the frequencies of each, and then we can calculate a mean and standard deviation based on those frequencies. And it's just coincidental that the standard deviations are the same. It's not coincidental that the means are close to the same, because this is our theoretical mean, right? It's what probability is telling us we should see, and then this is our actual, our experimental mean that we got from this large sample, and this is a pretty good size sample. If you add all those up, that's 50, 60, 70, 80, close to 100, and then actually I think it is exactly 100, and then with a sample size that big, we should see the experimental getting close to the theoretical. So it's really no coincidence that those two numbers are similar. One thing to keep in mind when we're dealing with this stuff, and we've mentioned it before when we talked about probability, is the concept of something being unusual. So we still have that same idea of something being unusual or not, and we're still going to hold to it usually meaning it has to show up with a probability of less than 5% to be considered unusual. Okay, the key to a probability distribution is having a variable. In this case, we call it the random variable, the X, and that X has multiple numerical values. We're going to start off with discrete random variables. So the example we saw before with the number of kids, that was a discrete random variable, right, where X was the number of girls you had born to a family of 2 kids, and so you only had the choices of 0, 1, and 2. And then your probability of X is just what's the probability of not having any girls, and it was 0.25, and then the probability of 1 was 0.5, and the probability of 2 was 0.25. And that's all a probability distribution is. It's kind of like a frequency table, right? Before, with a frequency table, you would have instead of thinking of X as a random variable, X would actually be your data values, dot 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 dot, whatever you had, and then this would be the frequencies of them, right? How many you had of each of those values. So it's very similar, only now we're dealing with probabilities. So the difference between a discrete and a random variable, well, discrete and continuous random variable. A discrete random variable has to have a finite number of values, countable. It can be really, really big. You could have 1,000,000 different outcomes for your random variable, and it would still be considered discrete, as long as it was countable. A continuous random variable is something that has infinitely many values, things that we cannot count. Usually think about there are no gaps in between one number and the next. Discrete random variables are usually whole numbers. They don't have to be. They could be half numbers and quarter numbers and things like that. But as long as there's gaps and they're countable, then it's still considered discrete. So some simple examples would be, well, basically, discrete random variables are normally whenever you have numbers of things. Something that could answer the question, how many blank? And you say, well, there's 5, there's 70, there's 1,000,000. Countable numbers. Continuous random variables are usually something that measures not a quantity, but more of a measurement. I know that seems a little vague, but measurements of things like distances, right, or volumes, things that can have infinitely many measurements. A distance can be measured as precisely as you want, whereas a number of things, it's only one or the next. With probability distributions, we still have the same rules that probabilities have to be between 0 and 1. So rule number 3 is the same rule that we always have for all probabilities. That this is just saying each probability is between 0 and 1, and it can be inclusive. So you could have a probability of 0 and you could have a probability of exactly 1. But if you had a probability of exactly 1, that would be the only one you could have, because the other rule is the sum of all the probabilities must add up to 1. And that's a biggie. And then of course you have to have a numerical random variable x, and its values are associated. So you just have to have some x and then all the px's that go with it. Here's a nice pictorial example of a probability distribution. This is called a probability histogram, and it's just like any other histogram, only now we're dealing with probabilities. So before we had on the vertical axis, first we started off with frequencies, right? Just the number of times something showed up. Then we went into relative frequencies. Remember those? And those were normally listed as percentages or decimals. Well, isn't a probability the same thing as a percent or a decimal, right? Isn't 0.3 really the same thing as 30%? So this is really just exactly like a relative frequency histogram. What kind of data is this down at the bottom? If we're talking about these numbers here, this is your x, and it represents the number of jurors that are of Mexican American descent. And so your choices are from 0 to 12, because a jury is made up of 12 people. So is this discrete or continuous data? And you go, well, of course it's discrete. We're counting numbers of things. Some very simple formulas for calculating our mean and our standard deviation. I wouldn't really worry about these formulas too much, especially not, two different formulas for variance is just silly. The mean, that's a pretty easy formula to do. You've got x times its probability, and then you just add all those up. These also aren't so bad, and they're pretty easy to do by hand if you're using Excel and things like that. But we've got technology, right? Calculators, SAS, SPSS, StatCrunch, whatever you want to use. We've got all sorts of easy technology tools to do these for us, so don't get caught up in the formulas. The expected value is just the word that we normally use to describe the mean of a random variable. It is the actual mean of that random variable, but it kind of makes more sense to call it an expected value rather than a mean, because a mean kind of has a connotation of an average of things we already have, whereas remember, a probability distribution is like a crystal ball, right? It's telling us the likelihood that a certain value should show up in the future. So our expected value is telling us that average value we would expect to get in the future. So that's just the only reason why we call it something different, and it makes a little bit more sense to call it an expected value. So whenever you hear expected value, they're just talking about the mean of that probability distribution. Here's a simple example. We've got the x and the probabilities from that example of having 2 children, and x here represents the number of girls. The first thing we would do is calculate x times p of x. So this next column just represents all of that, right? It's each of these times this. And then the next column is doing this work, right? But first, in order to do this, we need to know what the mean is. And as we saw before, the mean is the sum, right, of all x times px. So we had to add all these up. We got 1. Again, that's just a coincidence that it's a 1. I mean, it's not a coincidence because of this setup, but your mean is not always going to be 1, obviously, which makes the math a lot easier here. So now to do this one, you would take x, right, which is 0, minus 1, square it, and then multiply it times its probability. You can see how it's not too difficult. I mean, it's pretty easy math, just a simple subtraction, a square, and then multiply by a number. Very easy math to do, very easy to do in Excel, but technology does it for you much better. So there we have it. This is the mean, right? This is the variance. And so to find the standard deviation, we have to take the square root of it, and we get a standard deviation of that 0.7 that we saw on the previous slide. Just like before, our unusual results are anything that are more than 2 standard deviations away from the mean. So if we take that mean that we calculated and go plus and minus 2 standard deviations in both directions, that'll give us the idea of unusual results, which doesn't really make real good sense for this example, because if you remember, our mean was 1 and our standard deviation was, let's just make it 0.7 for the math to be easy. So 2 times the standard deviation is 1.4, right? So if we add that to 1, we get 2.4. And if we subtract it from 1, we get negative 0.4. And that tells us that that should be the range of normal results, right? Usual results. And this is the range of x. So if x is outside that range, it's considered unusual. Well, what were the actual possible values for x? If you don't remember, I'll remind you that x was the number of girls you could have when you have 2 kids, and it's either 0, 1, or 2. So no duh, something smaller than negative 0.4 would be unusual, because how can you have negative children? And then something bigger than 2.4 would also be quite unusual, since the maximum was 2. So this is a very silly example of unusual only because our random variable was so small, right? It only had 3 values, 0, 1, and 2. When we start working with more realistic data with bigger ranges, you'll see that this range rule of thumb actually does make sense. This is just formalizing what I said before, kind of silly. Okay, the rare event rule is very similar to the unusual rule. It's just another way of stating that if we're living in a certain world under certain given assumptions, it would be very unlikely to experience a certain outcome to an experiment. So in this particular example, we're talking about the assumption we're making is that a coin is fair. It's fair balanced, you know, that it should come up heads and tails evenly. So we would imagine it would be extremely unlikely, not impossible, but extremely unlikely to toss that coin 1,000 times and get 992 heads. Because that's just way off from what you would expect. You would expect somewhere around half, right? Somewhere around 500 heads. Now, obviously, 505, it wouldn't be a big deal, and even 600 probably wouldn't be that unusual. But if we worked out the probability of 992 out of 1,000, we would see that it would be very, 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 very tiny. And it all comes back to the probabilities. So a rare event is not just something that seems rare. We actually have to work out the probabilities, and that probability has to be small enough for us to consider it to be rare. And usually small enough means less than 5%, but again, we can set that to whatever level we want. And so identifying those unusual events, like I said, comes back to just finding those probabilities that are smaller than something. So whether it means getting far more results than we expected or far fewer results than we expected. It's always going to come back to what's the probability of that result. And when we're dealing with random variables and probability distributions, it's not just the probability of that number of things. It's going to be that number of things or more if we're looking for something that's unusually high, or that number of things or lower is usually what we're going to do. We could actually talk about the probability of exactly 992 heads, but it's more often that we'll talk about what's the probability of getting 992 or more heads out of 1,000 flips. Okay, or if we think getting 100 out of 1,000 is really small, we would ask for what's the probability of getting 100 or fewer out of 1,000. Okay, that's probability distributions.